Hello everyone. So welcome to the mind map of this particular chapter in which we will talk about magnetism and more specific towards the magnetic effects of current. First of all, we already know that magnets had been existing in nature and humans had been aware of the magnets, but and they had been used in the magnetic compass and all. But with the invention of electricity, we had wires running across the streets carrying some current. What was observed that whenever you try to bring a magnetic needle close to a magnetic current carrying wire, then it used to behave abruptly, maybe turn in other directions. It is not supposed to turn in other directions, right? It should always point to the north, magnetic north pole of the earth. But it was found that when you take the this magnetic needle to the in some presence of the current carrying wire, in the vicinity of current carrying wire, then it will experience some force. Then uh, by the time we already knew that in the nature, only when two magnets are there, they could exert force on each other. There is no way any other force could be exerted on this one. I mean, maybe from electricity and all, but only when you bring two magnets, they will attract or repel each other. And that is the case which is happening here. So it means that this wire must be creating the same thing that this magnet is creating, that is magnetic field. So here born the branch in which we will talk about the magnetic property of electric current. In this, we'll first talk about this one, Bayard-Savart law. What this Bayard-Savart law was, it basically talks about this phenomena, and it says that let's say you have a current carrying wire. Then what you take is, take a very small length dl length. Let's the current is going upwards, so the element that you have taken, I'll use another color to define it, will be in this direction, right? So take that element, and due to that element, जो भी उससे magnetic field create होगा at some distance, which is maybe l distance away or r distance away, then the magnetic field at this point P could be given with the formula that was given by Bayard and Savart, which is B is equal to mu naught by 4 pi, which is a constant, and uh, IDL cross R upon R cube. So, what is this mu naught? Mu naught is a constant which is called permittivity. Permeability. Permeability of space. In the previous chapters, we had already talked about something called permittivity of space, which is called epsilon naught. There is this relation between epsilon naught and mu naught, that the speed of light is equal to under root, or 1 by under root is equal to 1 by under root of mu naught epsilon naught. So if you are ever confused that what is the value of mu naught, you can just plug the value of epsilon naught and see, and from this equation you can get the value of mu naught. That is the constant that comes up in the equation, which is called permeability of space. If there is some other medium through which the magnetic field is passing, then mu will change according to that medium. And what is I here? I is the current, and dl is the length. Dl is this length, and when you multiply I into dl, what we call this is equal to the current element. It is simply this current multiplied by the small elemental length, that is called dl. So, and this is cross multiplication. So obviously these are two vectors, and you already know that the cross multiplication, when you do cross multiplication of two vectors, it results into another vector which is perpendicular to both of them, right? You could even write it in another format, that b is, or dv. Why I'm calling this dv? Because it is going to be a very small field generated due to a very small element of the length. So db is going to be mu naught 4 pi I dl cross r cap divided by r square. I have just switched r by r cap upon r cube is equal to r cap upon r square. R vector upon r cube, it will simply get rid of uh, one of the magnitudes of r, and that's why only r square will be there. So either this formula or this formula could be used. These are very fundamental formula, because we are talking about dB here, right? Not the complete. So what you will do is, in multiple cases, whatever length, let's say it is a ring, let's say it is a straight line, in all of them, let's say I'm talking about this point, then you'll calculate the magnetic field due to this elemental length, due to this elemental length, due to this elemental length, and adding them up with appropriate limits will give you the net magnetic field. And that is how we derive. वैसे ही हम derive करते हैं, क्या करते हैं हम, कि एक छोटा सा एलिमेंट लेंथ लिया dl, एंड लेट्स से द करंट इज फ्लोइंग इन दिस डायरेक्शन, तो करंट अगर इस तरफ फ्लो कर रहा है तो हमारा एलिमेंटल लेंथ जो होगा उसका डायरेक्शन ये होगा. Of course, elemental length or elemental current is always going to have some direction. That is why it is a vector quantity and it can have cross multiplication as per the Biot-Savart law. So उसको इस छोटे से एलिमेंट की वजह से जो मैग्नेटिक फील्ड बना यहाँ पर, वो हम लेंगे. फिर इस छोटे से एलिमेंट की वजह से मैग्नेटिक फील्ड जो यहाँ पर बना उसको ऐड कर देंगे. ऐसे ऐसे करते गए, अगर छोटा छोटा करते गए, तो इट इज नथिंग बट इंटीग्रल, राइट? इंटीग्रल में ही तो करते हैं, छोटा छोटा लेंथ ऐड करके टोटल बना देते हैं. So it is going to be integral of this formula, which will give you the total magnetic field at any point for different situations. For example, अभी यहाँ पर हमने ये वाला पार्ट डिस्कस कर लिया है. हाँ, see, it is simply the same equation that I gave in a slightly different format. हमने C को वहाँ लेफ्ट हैंड साइड रखा हुआ था, एंड now of course this is perpendicular, so it will give you a resultant in the perpendicular direction to both of them. ये फ्लेमिंग्स राइट हैंड थंब रूल से भी फाइंड कर सकते हैं. अगर करंट कैरिंग वायर ऊपर की तरफ जा रहा है, इफ द करंट इज फ्लोइंग अपवर्ड्स एंड दिस इज द वायर, प्लेस योर थंब in the direction of flow of current, and the curl will determine, see, the curl will determine the direction of magnetic field. Let's say at this point I'm talking, then the curl is facing in this direction, right? So the magnetic field is going to be in this direction. While let's say if the point is this, then it is going to be in this direction. So whatever curl denotes, जो भी कर्ल जो हमारा हाथ का है फ्लेमिंग रूल्स के हिसाब से, वो डायरेक्शन पॉइंट करेगा मैग्नेटिक फील्ड को. सो दैट इज बायो-सावर्ट लॉ. लेट्स कम टू द मैग्नेटिक फील्ड फॉर ईच ऑफ द स्पेसिफिक पोर्शंस. सी, ये है एक स्ट्रेट लाइन, और मे बी एट एनी लेंथ इट कुड बी गिवन, एंड इससे हम कोई भी पॉइंट जो है P r distance away, the shortest distance from the straight line to the r to the wire, this is the wire carrying some current I and having radius r, or the distance between them r, then what is the magnetic field going to be at P point? It is simply but B at P is going to be mu naught I by 4 pi r. I have used the term r here, so r, and sine alpha plus sine beta. It is more easier to remember than rather than cos theta 1 and cos theta 2. इट्स जस्ट कि इस इक्वेशन में यहाँ पर थीटा 1 एंड थीटा 2 कंसिडर किया है, बट आई विल गिव यू मच बेटर that this is going to be alpha and beta. So take these two angle and you will be having much more easier equation to remember, this one. So rather use sin alpha and plus sin beta. Now yes, we can use this one. See, so this one we have already dealt with. Now magnetic field at the center of a ring, or the I'll use more general part. Let's say this is a current carrying wire of radius r, maybe carrying current I. Then the magnetic field at any point which is x distance away from the center at the axis, that is going to be from this formula. B is equal to mu naught I a square upon 2a square plus d square upon 3 by 2. Okay, and if you do want to find out at the center, it's just that the d is going to be 0 and you will be left with this formula, because it will be up on the upper hand side, it will be a square, and on the lower hand side it will be 2a cube. So a square will get cancelled out and you will be left with this formula, where mu and I you already know. Mu naught, that is permeability, and 2a, a is the radius, you can even write it as a. So this is the formula for a ring. This is an unnecessarily it's not that important, you can just let it be. Now in a solenoid, what is going to be, see, solenoid is nothing but a coil. We already talked about that. For a ring, magnetic field is going to be passing through the center very in a strong manner. Then what we do is basically we try to generate multiple turns, and this is called a solenoid. At the center of the solenoid, this magnetic field is going to be B is equal to mu n I. Mu is the permeability of the material inside the solenoid, it could be any material. So, and n is the number of turns per unit length, and I is the current. At the end, or at the at one of the ends, or any of the ends, this is center and it is the end, it is going to be mu n I upon 2. So that is for the solenoid. We have another thing called toroid. It is simply that it is a straight line, right? The cylinder is in a straight line. If the cylinder is in I should rather make a hollow thing first, because a toroid is always based on some frame, a circular frame around which coil is wound. This is a toroid, and the magnetic field at the center, at the central line, is going to be from this equation, toroid. B is equal to mu naught Ni upon 2 pi r, where r is not this radius, not this radius, but the radius of this thin pipe. If this is going to be the diameter of the pipe, then the radius is this one. This is the r that you have to plug in this equation. So that was for the toroid. Let me see if any other one. Yeah, I think we can go ahead with the more general equation called Ampere's law. In the electrostatics, we had discussed about Gauss's law, in which we had integrated the whole electric flux, and then it was equal to Q upon epsilon naught. In a similar manner here, Ampere's law integrates B dl is equal to mu naught I, where B is the magnetic field and dl is the length. So it is basically we are integrating. अभी उस चैप्टर में हमने इंटीग्रेट किया था उसको ओवर द एरिया, दैट इज व्हाट द फ्लक्स वाज. बट हम यहाँ पर क्या करते हैं, लेट्स से इस पाथ में हमने मैग्नेटिक फील्ड कैलकुलेट करना है. लेट्स से दिस इज द वायर एंड यू हैव टू फाइंड एट द रेडियस आर. देन रेडियस आर पे हमारे तो बहुत सारे पॉइंट्स हो सकते हैं एंड दे विल फॉर्म अ सर्कल एंड सब पे मैग्नेटिक फील्ड सेम होगा. सो यू कैन सिंपली मल्टीप्लाई b इंटू टू पाई आर, दैट विल बी द this part, this part, and that should be equal to mu naught I. So from here you can get the magnetic field. All right, that is called Ampere's law. So you can this is more of a shortcut rather than derivation, and you can use this very frequently. Now coming to, I think, forces. Yes, let me discuss here. Yeah, now if there is a wire carrying I1 and there is another wire carrying current I2, then what do you think? They will form a magnetic field in this manner, right? According to Ampere's law, and another magnetic field coming in this direction and going in this direction from the second wire. Don't you think these magnetic fields are coming in contact and they are interacting with each other? That is exactly what happens in the magnets, right? So a magnetic field line in this direction and another magnetic field in this direction. So what happens is, due to them some attraction between the wires exist, and that is F is equal to mu naught I1 I2 divided by 2 pi d, where d is the distance between them. All right, so this is going to be the formula for the force per unit length. This is not the net force, force per unit length. And there's this one thing that I should tell you, that whenever the two parallel wires, this should be parallel first of all, whenever the two parallel wires are carrying the current in the same direction, this is going to be attractive force, same I, and repulsive force when you have opposite direction, opposite current. I hope this is clear. So this was the force between this this part. Now let me discuss some other portion. Let me discuss about maybe we can discuss this one first, because it is very much related to what we had discussed. Of course, I think magnetic field, we have already talked about it. The unit is Tesla. SI unit is called Tesla, and there is another unit which is called Gauss, where 1 Gauss is equal to 10 to the power minus 4 Tesla, because 1 Tesla is very high magnetic field, and we generally in our surroundings we have less magnetic fields. So that is why a Gauss is a more practical unit, where Tesla is a SI unit. Now coming to this portion, which is the force due to a charge. First of all, why was there a force between them? Because there were two magnetic field lines passing each other. Now let's say yes, magnetic field line is also there. What I'm representing from cross is the magnetic field going inside the loop, inside the plane. And whenever I give you a field having this this type of representation, It basically means that magnetic field is coming out of the plane and this is going inside the plane. It could be in either form, either surrounded by circles or just plane. Now, the magnetic field is going inside the plane, and let's say another charge is moving in this area. It is moving in this direction. What is happening due to this movement? Of course, due to this movement, isn't it very similar to the current carrying wire? Because current carrying wire is simply charges moving inside a conductor. So it is due to the movement of charges that the magnetic field exists. Now there is this charge also moving inside a magnetic field, so it should also generate some magnetic field around it, right? And which will interact with the original magnetic field that I have given you. So basically what it tells is, whenever you have a charged body passing through a magnetic field region, then the force which it experiences is equal to Q B cross V. Again, there is this cross multiplication, which is the cross product of two vectors. So in this case, if this is the velocity, this is the velocity vector, and this is the inside is the magnetic field vector, then what you do is basically make it cross product. So the cross product will go downwards, right? The resultant is going to be perpendicular to both of them, so it could be either up or downwards, but according to the cross multiplication rules, it is going to be downwards. You can use right hand thumb rule, all of that, to determine the direction. Then what is happening over here? Due it is moving in this direction and the acceleration is going to be perpendicular to that. Do we have some motions like this in which the particle is moving in some direction and the acceleration is in this direction? Of course, it is going to be a circular motion. Why? Because the moment it turns, due to this acceleration, the resultant of B cross V is going to be in this direction. Why? Because B is inside the plane and now velocity is here. So it is always going to be perpendicular to the velocity and having a fixed value. That is why this particle is going to perform a circular motion. All right. So that is the motion of the particle, a charged particle inside a fixed magnetic field. And if the case in which the magnetic field is parallel to the velocity, in that case what will happen? Simply, what is B cross V? It is simply BV sine theta. What is the angle between these two vectors? 0 degree, and sine of 0 is 0. So no force will be acting on particles which are having the velocity in the same direction as the magnetic field. But जहाँ पर magnetic field perpendicular हुआ velocity से, तो definitely वहाँ पर circular motion होने लगेगा. Whether the circular motion will be complete or incomplete, it depends on the region of the magnetic field. Let's say the charge is here and it wants to do a magnetic circular motion, but यहाँ पर magnetic field खत्म हो गया, तो यहाँ पर सीधा tangentially move करेगा. But over this region, over this path, it was actually performing circular motion. तो हम क्या करते हैं कि assuming that it completed a circular motion, we can find the radius of the circle and other factors. So how can we find the radius of the circle? Again, we can talk about F. Let's say there's this ball of charge Q and mass M. Then अगर हमें force पता है उस body पे जो लग रहा है, perpendicular force or centripetal force, then we can quickly find out the acceleration. Acceleration is nothing but F by M, which is going to be QBV upon mass, right? So this is the acceleration. Is acceleration always equal to V square upon R in case of circular motion? Of course. So that should be equal to QBV upon M. one of the v gets cancelled out, and you're left with r is equal to mv upon qb. This is going to be the the radius of this thing, radius of the curve, or radius of the circle in which the particle will move in this motion. We can also find out the time period, right? Time period, of course we can. Why? Because time period is simply, let's say we talk about one circular motion, one turn, one rotation. In that, what is the time taken is simply the same time as the time period, and उसमें distance कितना cover करेगा वो body? That should be equal to the 2 pi r, the periphery, the circumference of the circle. So velocity is equal to length divided by time, right? Time period. So time period is nothing but 2 pi r upon v. We can find out, let's plug the value of r from here. It's going to be mv upon qb upon v, isn't it? Wait. This is the radius and this is 2 pi r and v. So v gets cancelled out and you're left with 2 pi m, or 2 pi m upon qb. That is going to be the time period of this motion, circular motion. Do we need more details on this one? Yeah, so this was time period. Frequency is simply 1 by time period. And I think we also talked about this one, that if it is perpendicular or sorry, it is parallel or anti-parallel to the direction of the motion of the charge. If that is parallel or anti-parallel, it means opposite to the this thing, opposite to the direction of the magnetic field, then it is going to be 0. And this helical path, I'll talk about it. Let's say the magnetic field is in this direction, the magnetic field is in this direction, and the velocity of the particle is in this direction. So uh, one component of the velocity, this is the velocity, this is one component v1 and this is another component v2. Due to this second component, since it is parallel to the magnetic field, there will be no force. But due to this velocity, there is going to be a force, right? There is going to be a force because it is parallel to the magnetic field line. So due to which it will perform circular motion, but at the same time the v2 velocity is not going to change. So in the you can consider this to be a circular motion, but having a fixed velocity in this direction. So it will be something like this. Circular motion, but at the same time it is going up as well. So this is called a helical path. Helix. This sort of geometry is called a helix. That is what this mind map is talking about. Again, R is going to be the same, mv1. v1 is the component which is perpendicular to the magnetic field. v1 is the component which is perpendicular to the magnetic field. And yes, pitch, what is pitch is actually the distance in the other direction. Let's say the rotation is happening, then in what in each rotation, what is the distance which it is covering, since it is also moving in the upward direction. So एक रोटेशन करते समय वो अपवर्ड कितना डिस्टेंस मूव करता है, दैट इज कॉल्ड पिच. This point and this point, you can easily find this one. Any 2 points will do. It is going to the pitch. So we can definitely find out why, because we have the time period. What was the time period? 2 pi m by qb. 2 pi m by qb, and we already have the second velocity v2. v2. So v2 is going to be the distance covered divided by the time period, right? Because it is going to be the, अभी ये मोशन करते हुए, एक रोटेशन करते हुए उसको कितना टाइम लगा? उसको टी टाइम ही तो लगा, टाइम पीरियड, तभी तो हमने वो प्लग किया है 2 पाई m by qb. So d is going to be 2 pi m vb, or v2, I should call it v2, divided by qb. v2 is the velocity in the direction same as the magnetic field. I think that should be the same thing here. Yes. तो ये वाला काफ़ी इंटरेस्टिंग मोशन था. एंड कमिंग टू, आई थिंक वी हैव ऑलरेडी डिस्कस्ड दिस वन. Yeah, it is simply this one. I think we already talked about this one, that two wires attracting or repelling each other. For that, a more general equation could be this one, that the force on one of the elements, let's say this is an element, it is going to be simply ideal cross B. Ideal is going to be a vector quantity. This is going to be is equal to df. So integrating all this over this whole length is going to be give you the formula which I talked about, this one. All right. So if all that is clear, I think yeah, we have covered most of it. One portion that we are going to discuss is this one, but it is also, I think, in the second part as well. Yes, we can take it from here. Now let's talk about magnets. We have something called a north pole, we have something called a south pole. Do we have unipoles existing? For example, in the case of charges, it was maybe a plus charge or minus charge that was existing independent of the other charge. But magnets में हमारे पास unipoles नहीं होते हैं. There are always dipoles. अगर हमने इसको break भी कर दिया बीच से, तो it will form two different magnets, but it will have poles like this. कितना भी further break कर दो, north pole south pole रहेगा ही. So in case of charges, I think we had talked about something called dipoles, electric dipoles, in which there was this positive charge q and there's minus q, another charge, and fixed to each other with some material which is non-conducting of the charge, having d length. Then electric dipole was defined as qd, right, having the direction from negative to positive. But यहाँ पर हम कैसे define करें magnetic dipole? Can we just take the length? अगर लेंथ लिया तो हमने q की जगह क्या डालेंगे? What will be placed in instead of q here? Because we do not have magnetic unipoles, right? So it is not defined in this manner. It is just the intensity of the magnet that determines, and the length of the magnet. It is not something we actually derive. It is more of a practical thing, that there is this term m, just a second, m, which is equal to magnetic dipole or magnetic dipole moment. So this is the magnetic dipole, which it represents the length and both the length and the strength of the magnet. Of course, the lengthier the magnet, the more strength it will have. So abhi ye dipole, let's consider this, any magnet is going to be a dipole. First of all, let's place it in the magnetic field maybe magnetic field is in this direction, external magnetic field. And due to this magnetic field, this north pole is going to experience a force here, and this south pole is going to experience a force here, right? Of course, अगर magnetic field ऐसा होता कि this is the dipole and तब magnetic field दे दिया हमने, अगर north था ये south था, तो of course the magnetic field lines are like this, right? Entering from the north pole and going to the south pole, and again traveling inside the magnet, and then coming emerging out of the north pole. This is the direction. So अगर हमने यहाँ पर मैग्नेटिक फील्ड अपना दे दिया, तब तो ये रिपेल करेगा, रिपेल। और हमने अगर इसको साउथ बोल दिया और इसको नॉर्थ बोला, तब they will attract, the external magnetic field will attract the magnet and it will try to move in this direction. But what happens when you have magnetic field which is perpendicular to the north and south pole directions? Then this north pole is going to experience force in this direction, and the south pole is going to experience force in this direction. What happens when, and they have the same force, equal. What happens when two forces are applied which are equal to each other in the opposite direction? The net force is zero. Of course, you can say that net force is zero, but is it really not going to move in any fashion? It is going to, right? Your instinct will tell you that it will try to rotate about this axis of rotation or point of rotation. अगर ये rotate कर रहा है, तो of course it should have experienced some torque, right? क्योंकि हमने पढ़ा था in the chapter of rotation, we had talked about something called torque. अगर कोई बॉडी पे फोर्स लग रहा है perpendicular to the length from the point of fixing and the point of application of the force, then we have something called torque, which is responsible for rotation of the body. There are two motions, translation and rotation. We are talking specifically about the rotation part. This is called torque, and torque in this case is going to be simply M cross B, where B is the magnetic dipole strength and B is the magnetic field. I should call it external, because magnet itself has some magnetic field also. So it is in the presence of external magnetic field that these two magnetic field lines interact with each other and they produce a torque. So torque अगर मिल गया और उसका मास अगर given है, तब हम उसका rotation के बारे में predictions कर सकते हैं, right? The more important thing is torque. The questions may be indirect, that this is the situation and you have to find the angular velocity and things like that. That you can do based on the formula that we have talked about in the chapter of rotation, but for that you will always need a torque to find the torque, and torque will be calculated in this direction. Of course, it is again cross product of two different vectors. This magnetic field or magnetic dipole is going to be a vector quantity from south pole to north pole. This is going to be the direction of the dipole, magnetic dipole. So fine. Now again, coming to the same situation, I'll use another color to yeah. So this is going to be the magnetic field and this is the dipole, the same dipole. Now it is not having any energy right now, but the moment you let it free, then this force and this force creates a torque, due to which this whole magnet starts to rotate. Now in the chapter of rotation, we already talked about that whenever you have some rotation, there should always be energy associated with it, kinetic energy, right? I omega square, sorry, was it half I omega square? Yes, half I omega square. So this was the kinetic energy of rotation, of pure rotation. Again, we have some rotation over here, and some moment of inertia should also be there for the magnet. It is having some mass, it is having some length, then moment of inertia तो उसका भी होगा ना, तो हम वैसे हम find कर सकते हैं, right? This is going to be the kinetic energy. So omega can be easily found out because torque से हमें मिलेगा angular acceleration, and angular acceleration से this equations of motion you already know that omega final is going to be equal to omega initial plus alpha t, right? Similar to the equations that we have in translation. Let's not go further from this. Let's try to be in this situation. And what I was trying to talk about is it must have some energy associated with it, right? And energy cannot come from nothing. It should come from one form to another. अगर यहाँ पर kinetic energy gain कर रहा है in the rotational motion, then it should have some energy stored inside the system. So that is called potential energy. Potential energy of magnets. As we had in gravitation, as we had in electrostatics, we have some potential energy related with the magnets as well. So potential energy of magnet, to be more specific, the situation in which we have a magnetic dipole in the presence of another magnetic field is equal to minus m dot b. All right, and this is the dot product of two vectors, which is the, if you talk about the magnitude, it is going to be mb cos theta, right? So this is the potential energy, and we can find the change in potential energy in two orientations, and we can definitely find out the change in kinetic energy due to that, or change in potential energy, which will convert it into change in kinetic energy, and you can find the rest of the question whatever it is. So this was the topic we were taking. Now coming to about this revolving electron, it is not actually apt at this location, because we already have this concept in the chapter of atomic structure and Bohr's model. So we will take it up there. This part we will discuss there. Now there is this magnetic dipole. Let's talk about it. If we have, or I think I should draw it here. If we have a magnetic dipole having some magnetic dipole strength of m, then at any position p, yes, let's talk about the first position, which is maybe on the line of the dipole. On the line of the dipole, if we have any position which is a, then the magnetic field at this position is going to be this much, mu by 4 pi, mu naught by 4 pi 2m upon d cube, where d is this distance. D is the shortest distance between the, or sorry, d is the distance from the center of the dipole and the point A. At this point A, the magnetic field could be found out in this manner. Now talking about this one, that on the bisector, this is on the axis, right? On axis of magnet or magnetic dipole. In the bisector of the magnetic dipole, BP is going to be this much, m upon mu naught by 4 pi upon m upon d cube, and this is for a long length. If d is much longer than this length a, the length of the dipole, if it is similar, then this equation could be applicable. D plus L, the whole thing over 2 by 3, 3 by 2, sorry. But in most of the questions that you deal with this type of questions, magnetic dipole, you will be given this condition that D is much greater than A. Okay, I think we have covered the left portion, yes. Now we have something called, yes. What we do here is, at any position, at any position on the earth, this is the equator, and let's talk about here any point, then magnetic field is going to be in some direction, right? Let's say it is in this direction. Now let's say I have a current carrying wire here, then magnetic field due to this current carrying wire is going to be in this direction, right? Inside the this thing. Then what it happens is, let's say you have a magnetic meter, then the net magnetic field is going to be in this direction. Then this angle, whatever angle, say, see, if this was not existing, then this was the original field, original direction of the magnetic field. Now the net magnetic field is in this direction due to this another source, which could be any source. Then this is B net, and this is B uh, earth, right? Earth's magnetic field, or horizontal magnetic field of the earth. And this is the B external. Then this angle through which the direction of the magnetic field in towards the earth's original magnetic field, and whatever angle it has changed, the net magnetic field, that is called angle of dip. And if you talk about it, yeah, tan, if it is called, let's say, sigma, tan sigma is going to be simply B external upon B of the earth, right? This one, horizontal component, yes. This is the angle of the tip. So basically, if you have a magnet or a magnetic compass pointing in some direction originally, and you have, let's say, brought uh, another field which is perpendicular to the original magnetic field of the earth, then based on the inclination that it has changed, you can find out the strength of the magnetic field, which is due to the external source, right? So that is the portion which is here. Of course, it is an extension of the same thing. I have found out the tan theta or tan sigma. You can find out cos sigma. Nothing big in that. So it's just that if you remember this part, it will be good enough. The rest of it, the total magnetic field, you can definitely find out. Uh, Magnetic field lines, we already discussed about them. Now coming to this part, yes, paramagnetism, ferromagnetism, and diamagnetism. Or maybe we can discuss this part over here, then it is going to be more better. See, there's one formula that you must remember. It is more of a formula question, that if you have a magnet in the presence of magnetic field, it is oscillating. We discussed about that, right? Oscillating due to this torque. Then what is going to be time period? We have a formula for that. Time period is going to be simply 2 pi upon I by mb. I is the moment of inertia, m is the magnetic dipole, b is the external magnetic field. This is the time period for such rotations. This you must remember. Now coming to this portion, this is going to be a slightly uh, interesting discussion. Let's say, yeah, let's say you have a material in which magnetic field lines are passing, B or B naught, and you have this material which can become a magnet in the presence of a magnetic field. For example, maybe iron in the presence of a magnet, it also behaves as a magnet. So don't you think the intensity of the magnetic field will increase in this magnet? Of course. So we'll call it Bm, or B magnetized, and this is the B naught. So B is equal to, B total is equal to B naught plus Bm, right? Now what we define over here is this part. It is actually some mistake in the typing. It is mu naught, B naught upon mu naught. So what we do is, basically, this B was formula was having something in the format of mu naught, right? Mu naught and rest of the things. So it was always proportional to this one, right? Mu naught, permeability of space. What we do is, we make it independent. Another, we defined another equation, or another variable, which is called magnetic intensity. Yes, it may be confusing, but yes, it is magnetic intensity. Intensity. It is not the same as magnetic field, but it is another variable which we define to make it independent of the mu. So it is either B naught upon mu naught, and it is also equal to B total upon mu of the material. See, first of all, I have to tell you that if it is getting magnetized, then mu of the material is already greater than mu naught if it is getting magnetized. So we cannot exactly put mu equal to mu naught. Mu is the permeability of the actual material, not space. Now we have the definition of magnetic intensity. Then there is this another definition, which is called intensity of magnetization. We will define it here. Intensity of magnetization. Hmm. Let's divide it, or we can convert it in the format of using this one. H is equal to B naught upon mu naught, and H is equal to B upon mu. So divided by mu, or wait, let's write this B in the format of H. It is going to be H mu, right? And this B in the format of this thing is going to be H mu naught plus Bm. How can you find Bm? Is another this thing, as compared to this variable, which is the intensity, or the magnetic intensity. We also have intensity of magnetization, of magnetization. What is this intensity of magnetization is, let's say, in the absence of another material, H was the, what we had defined, H was the magnetic intensity. Then in the similar fashion, or in the similar manner, we can define something called intensity of magnetization, because this is the magnetized uh, this is the magnetized this magnetic field, right? Bm, magnetized magnetic field. It is the magnetization which has created extra magnetic field. But similar to the definition of H, if I can write in this fashion, if B is to H, then the same is Bm is to I, where B is the original total magnetic field, H is the magnetic intensity, Bm is the intensity of magnetic field which is extra, which is the produced which has been magnetized, and this is called intensity of magnetization. So I hope you can follow this, that whatever relation between B and H is there, the magnetic field and the magnetic intensity, we have defined in such a manner that it is independent of the first one. In the same manner, we define intensity of magnetization so that it is independent of the magnetic field which has been created. So we can write it in the similar manner that Bm by mu naught is equal to Bm by mu naught is equal to I. Yes, I. So we can write it as mu naught I, right? Mu getting here, and that will be equal. Now divided by mu naught, you will be left with or maybe divided with h mu naught. That will be faster. H gets cancelled out, and you're left with here mu by mu naught is equal to, this whole thing gets cancelled out, 1 plus mu naught gets cancelled out, and you're left with I by h. Now this I by h term, this term, we define it as susceptibility. How much the material is susceptible to external magnetic field so that it can get converted into another magnet. It is given by the term chi. So mu is equal to mu naught 1 plus this term was called chi, right? So this is the same thing, I guess. That should be the here. Yeah, this one. And we already defined these two. It is m by, it is equal to bm by mu naught. That would be more helpful here. And susceptibility, we already defined this one, and we derived this equation. Now coming to the only last portion, in which this one. Now we have different type of materials. In the presence of magnetic field, how they behave. The one could be that if magnetic field is passing through it, it will try to attract a bit and then create a few more field lines. Another material could be in such a manner that it is highly magnetized. So whatever magnetic field lines are there, they will get concentrated here. Or the magnetic field, this material will try to attract all the magnetic field lines. And the other thing could be that it is not liking the magnetic field. So if the magnetic fields are there, it will try to it will not let the magnetic field pass through them. This is called paramagnetic, which is slightly magnetic. We can call it slightly magnetic. This is called ferromagnetic, which is the magnetic property of the matters or the some metals, for example iron, cobalt, nickel, that we already talked about. And this is called diamagnetic. These are the three materials. And of course the chi of susceptibility of this ferromagnetic is going to be much higher than 1. This is going to be slightly higher than 1, and susceptibility of this one is slightly lesser than 1. Okay, so this was the, and the examples you can take away that paramagnetism, aluminum, manganese, you already know about these trio. Iron, cobalt and nickel are the only ones which are ferromagnetic. And in the diamagnetic, which slightly repel the magnetic field lines, bismuth, copper, and this one Hg is mercury, right? Nickel is not here. I think there might be a typing mistake here. Nickel is not one of them. diamagnetic. Nickel is strongly ferromagnetic. So I think that was the mind map of this particular relatively lengthier chapter. We'll meet in the next one.